Okay, so the second video for today's last class is all about rusting, which is essentially the same as corrosion or the same as oxidation. These terms are essentially synonyms, okay? Now, if we're talking specifically about rusting, we're usually talking about the oxidation of iron. Many materials, of course, are made out of iron, like we can see down here on this old building, right? Or maybe you've got a barn or something like that on your farm and the metal rusts over time. Well, rusting is nothing more than a redox process. It is oxidation. And why is this sort of a bad thing, okay, for structural integrity? Well, the iron that's present in the metal is in the elemental solid form. And when it's oxidized, it's basically converted to either iron 2 plus and then subsequently iron 3 plus. Now these forms, the oxidized forms, they can form ionic compounds, but they're not necessarily structurally as strong as the iron metal. So the material kind of rusts away and holes develop in the walls of the structure, so on and so forth. Okay, so how does this work, and how can we prevent this from occurring? Actually, we're going to learn some strategies in this section of the lecture to prevent this from occurring and to protect our iron structures. So this makes it, I think, kind of practically useful. All right, so we know that iron rusting is essentially an oxidative process. And that first step, the iron 2 plus is formed. Now, as we've been talking about at some length, when you build one of these redox cells, you don't need to have the reactants in direct contact, as long as there's a wire or conductor to transfer the metals to where they need to go from what's being oxidized to what's being reduced. This works, right? Now, in the case of iron solid, that a solid can be this wire, okay? It doesn't necessarily have to look like a wire, be in the shape of a wire, but it's a conductive metal. So electrons can freely flow throughout that metal. So when the electrons are produced by the oxidation, those electrons can easily travel through the metal to a cathodic region. And generally speaking, the cathodic reaction, or the reduction, involves oxygen. Oxygen is very prevalent in our environment from the air, of course. And oxygen can be reduced into oxide, which is the O2 minus. So in O2, this form, the oxidation state is 0. It's the elemental form. But when we reduce it to oxide, it's O2 minus, okay? So that's the cathodic reaction, or the reduction that can take place. We know earlier in the semester, I think it was chapter 13, we talked about laws like Henry's law that predicted the solubility of gases in liquids. And sure enough, gases can dissolve into liquids, okay? In some cases, acidic solution might promote this, all right? So basically what happens is the oxygen gas can dissolve into moisture, water, and then it can be reduced, okay? Now, in a subsequent step for rust formation, after these iron 2 plus ions are formed, they can further be oxidized to iron 3 plus. So it turns out the oxygen or iron, aqueous ion, the ion, can have multiple different oxidation states. One is iron 2, another one is iron 3. So we can actually further oxidize it to iron 3 in the environment, the oxygen-rich environment. And this iron 3 ion is actually what is believed to be responsible for rust formation. Because what happens is the oxide which forms from the reduction can combine with the iron 3 to make iron 3 oxide and some hydrate of water, okay? Now, depending on the environment and the mixture in question, the exact composition of this rust can depend on those conditions. It's a little bit of a messy reaction, I guess you could say. But nonetheless, this is essentially what's going on when iron rusts. The moisture is important, not only for formation of this iron 3 oxide hydrate, but also having water and ions or electrolytes present. It really allows for more efficient charge transfer. Remember, we have to shuttle these electrons different places. And if we're working in a conductive solvent, such as an aqueous solution with electrolytes, that promotes current flow and thereby promotes rusting, okay? So this is basically the rusting of iron, the process that takes place. So a few reactions behind that. Now, you may wonder, is there anything that you can do to kind of prevent this from happening, right? It seems like it would be a nice practical skill to be able to prevent the rust forming on your barn or your nails or whatever it is that you need to prevent the rust from forming on. And there actually is a pretty easy way to do this, okay? Now, there's a couple different strategies to help us do this. The first one is probably the least effective. I guess it's easy, but it's probably the least effective. One strategy is just to cover the surface of the iron-containing item that you wish to protect. So whether that be a nail or a pipe or something like that, you cover the surface. Perhaps you paint it, okay? Now this works fine as long as that paint has a good structural rigidity or integrity. In other words, that paint layer is complete and total. It keeps the oxygen away, keeps the electrons, where they need to be inside the iron. But unfortunately, oftentimes the paint might scratch, might flake off, and when that happens, it leaves your metal object completely unprotected. So while painting might work if you keep up that coating, very often the paint degrades and the object just rusts anyway. So are there any other options? Well, fortunately, I'm here to tell you that there actually are, okay? One is called galvanization, and another one is called use of a sacrificial anode or sacrificial electrode. And it turns out that the fundamental chemistry behind both of these ideas is really, really similar. So I hesitated for a second to group them differently, okay? Just a little bit different implementation of the same idea. So let's talk about what this process involves, okay? Well, we'll consider sacrificial anode down here at the bottom. Let's just say that there's this pipe that's underground and you want to protect it from rusting because you don't want to have to dig it up every few years and replace a part because it rusted through. So how can we do that? Well, we can use a device called a sacrificial electrode or sacrificial anode specifically, okay? And all this is basically another piece of metal. This is shown in the figure right here, okay? It's basically another piece of metal, and this metal is just basically placed in electrical contact with the device that you want to protect. In that case, is the iron pipe. So you basically just let them touch. They're in electrical contact, so electrons can go in and out of either one. So how does this work, this sacrificial electrode? It doesn't make sense by just putting another metal on our iron that it would work, right? Protect the iron. But in fact, it can. It can if certain conditions are met. And the major condition is that this sacrificial anode must be easier to oxidize than iron. So there has to be a component in your sacrificial electrode which is easier to oxidize than iron. So that basically means that it should be below it on the table of the reduction potentials. Now, why is that important? Well, it turns out that in nature, these redox reactions, they involve transfer of electrons. And the reaction itself doesn't care where the electrons come from. There just needs to be electrons transferred. So the electrons could come from the iron when the iron's oxidized in the pipe, and if it does, that pipe will rust. Or the electrons might come from our sacrificial electrode. So if we take another metal and we put it in electrical contact with the iron pipe that we wish to protect, electrons from this electrode and the oxidation of materials in that sacrificial anode could easily travel into the pipe. And even if there's a reaction occurring over here at this junction, a reduction occurring over here at this junction, those electrons could simply flow through the pipe, get to where they need to go. The chemical can react over here, and our pipe remains unoxidized. Or in other words, it doesn't rust, because the electrons are sourced from over here in our sacrificial electrode. They just flew through the wire to where they needed to be. So if we make this anode or a sacrificial electrode out of an easily to oxidize substance, basically what will happen is all the electrons will flow from there into the pipe, and we can protect the pipe from rusting because the material of the pipe itself does not oxidize. The only thing that oxidizes is the material which is present in our sacrificial electrode right over here. All right, so that's kind of the basic working idea behind this. Because redox reactions proceed preferentially in terms of the easiest to oxidize substance will be oxidized first until it's all gone. If we put a very easily oxidized substance in electrical contact with this iron pipe, that easily oxidized substance will react first, and thus it will protect the iron inside the pipe. And that's why we call it a sacrificial anode or sacrificial electrode. Oftentimes it's a sacrificial anode because that's where oxidation occurs. So the electrodes are produced, they flow into the pipe and protect it. It's also sacrificial, meaning that over time, the material that makes up this electrode will get oxidized away. And that's by design. Something has to get oxidized for the oxygen to be reduced, as we talked about on that previous slide. So why not make it an easily oxidizable and cheap metal that we make this electrode out of? That way we can protect our pipe and we don't have to dig it up every other year to replace a part because it's broken. So that's the use of a sacrificial electrode. Oftentimes, the element zinc is used to make these sacrificial anodes and also to do galvanization, which I'll describe here in a second. Now, if you ever go to the hardware store, you may buy some nails or screws or something like that, right? In this case, it's nails. These nails might be galvanized. It's kind of usually an option that you can take when you're buying these nails. Maybe they're a little bit more expensive, but the box says that they're galvanized. What does that mean? Well, basically what it means is that those nails, which may be made out of some iron, have been coated with zinc. Okay, so usually what you see on the nail is that there's like this almost like a matte finish. It's like a white coating on the nail, and that's the galvanization. And basically what that is those nails have basically been sprayed with small little particles of zinc, and that zinc is our sacrificial electrode on the surface of the nail. So the nail itself is coated with the zinc. And the whole idea behind that is as long as that coating is present, the zinc will react and not the iron in the nail. So the iron will be protected and that nail won't rust as long as that zinc is present. Okay, so the beauty behind this galvanization or the galvanized nails is that easy to oxidize metal, usually zinc, is added to the surface of our nails to protect them from rusting, okay? Now, if you run out of the zinc in either case, that nail is going to start to rust or that pipe is going to start to rust. So it's important to maintain the sacrificial electrode and make sure it's in electrical contact with the object that you're trying to protect. But as long as you do that, this will work and it'll protect your iron from rusting, okay? So it's a really kind of a practical skill, I think, that you all can use in your daily, everyday lives to keep objects from rusting that you want to protect. Okay. All right. One more interesting thing while we're on this, we talked a lot about iron, but another interesting metal to talk about is aluminum. Oftentimes, objects that you do not want to rust or decompose are made out of aluminum. And what comes to mind for this would be like aircraft bodies, okay? Now, why is that, right? I mean, aluminum forms a 3+ ion. It seems like it might be a pretty reactive metal, and indeed, elemental aluminum is pretty reactive. It really likes to be oxidized to form that 3+ ion. So what's the deal with that? Like, why do we make parts that we want to put into the environment and protect out of aluminum? It seems like it might even be more reactive than iron. Well, it is very reactive metal, but there is a advantage or an interesting feature of aluminum to talk about. So elemental aluminum, Al solid, will readily oxidize with oxygen in the air. But that oxidation reaction occurs on the surface of the chunk of the aluminum metal, and really only on the surface. Because once the aluminum on the surface is oxidized to form aluminum oxide, it turns out that aluminum oxide coating on the surface of the metal is pretty inert. It's a pretty inert material that prevents further reaction of the aluminum. So you might say, oh, well, I've never seen an aluminum object rust. You got to be careful a little bit, because it turns out that aluminum will rust. It will form an oxide. It just doesn't form that brown rust-colored material that we're so familiar with iron. It forms aluminum oxide, and it does so in a very thin layer that strongly attaches to the metal surface and doesn't come off. And that thin layer actually prevents the further oxidation of aluminum, and it protects it. So I guess we've got to be a little bit careful with what we mean by rust exactly. Does aluminum react to form an oxide on its surface? Yes. It just so happens that that's good for structural integrity of the aluminum part, because it forms this protective layer that prevents it from degrading further. Okay? All right, so this lecture was all about corrosion, galvanization, and use of sacrificial anodes. It's kind of an interesting practical chemical skill, I think, that you can get out of this class for your daily life. One more